Hi, welcome back. So we're going to now continue what we're discussing, and we're going to try to perform the L2 estimates on the derivatives of nonlinearity using the LK operators. So here's a proposition of what we are able to accomplish. Okay, for any fixed k, so I'm going to fix some k now. Okay, there exists some increasing function h. Okay, with h of s equal to big O of s, meaning that h vanishes linearly as s goes to 0, such that for every j between 0 and k, okay, or j between 0 and k, and for all t bigger than or equal to 2, you have that the j derivatives of f, right, measured in L2 over spatially, this is going to be bounded by what? Bounded by h acting on, the input here is phi, right, measured in the curly E space with k over 2 derivatives plus d over 2 derivatives plus 1 multiplied by decaying factor t to the 1 minus d over 2, okay, and multiplied by phi to phi measured in ek. And it's provided the support of phi is going to be within this cone that we specified. The phi has a support property that t is bigger than or equal to x plus 1. Okay, so let's see how this relates to what we have written down earlier above. Right. So what we're going to do actually when we're treating look at this schematic expression that we have written down here. Let's let me actually erase some of the things, and then we'll copy and paste it so we can do some annotation. And let's do it like this. Good. Okay, so now let me take this and copy it, and then copy, and then go over here, paste. Okay, so we have something like this, right? This is what we have before for LK of f. So I want to put this in L2. Oops, let's use a pen. That's helpful to use a pen to write. So I'm going to put L2. So what I'm going to do is I'm going to put this term in L infinity of RD. I'm going to put this term in L2 of RD. Right. And so let's see how can we estimate this term in L2 in RD. We have up to k derivatives acting on phi. We're going to measure in L2 in RD. And remember, this phi term only shows up if I'm in the Klein-Gordon case, if m is positive. If the mass is 0, we have assumed our nonlinearity to not have this phi term. So when mass is positive, this phi term shows up, and we can estimate it using what we had before. Let's see the energy estimate here. This first one here, we have the L2 norm of k up to k derivatives is going to be bounded by what? By phi in ek. And similarly, right, if we have Lk of the derivative, this is for both wave and Klein-Gordon term, this is going to be bounded by phi in ek also. Right? This is the rectilinear energy, the energy relative to the constant t slices. Okay, so going back to what we have down here, where is it? Over here, right? We see that we have up to k derivatives acting on phi or d phi, and therefore this is going to be bounded by phi measured in the ek term, and this is precisely the ek term that comes out over here. Okay. Now the key question is, how do we control g? What is g? Now g is so g here schematically is some smooth function. Remember, g is a smooth function of up to k over 2 derivatives of phi and d phi, right? Okay, so basically what we're just saying is that, so g, right, so if we're going to, so this means that the g can be, so if g is a smooth function of up to its different derivatives, we can take its argument, plug the argument in some norm, and then we can say g is bounded by some increasing function of this norm. Okay, and that's what we have. We have that. So h here, right? The function h here this is an increasing function. This is basically just an upper bound for g, right? So what we have is that this tells us that g of its arguments is bounded by h of the norm of the arguments. Okay, and this is the L infinity norm of the arguments. Okay, and so then this h has to be increasing, right? Because even though if g is undulating, right, what we're trying to do is that we're going to say that everything we plug in with at most this norm is going to be bounded by this. So for this to be a good upper bound, it has to be increasing. Okay, so now the question is L infinity norm. Now since we're looking at up to k over 2 derivatives of phi and dphi, we're going to measure this in L infinity. This means that based on our L infinity estimates earlier, pointwise estimates, right? And again, we're in a situation where we're looking at see in both situations. So in the case of the Klein-Gordon equation, right, we have these phi terms that shows up, and then we know that Lk of phi is bounded by the energy of k for derivative plus d half plus 1. In the wave equation case, you also have the same space on the right hand side. And it's because that in the Klein-Gordon case, as I said before, we're using the mass term to do the estimate, and in the general case, we're using the kinetic energy term to do the estimate. And kinetic energy controls one higher derivative, so we're not losing any derivative here. So the derivative term used is exactly the same, right? What's different, however, is the decay rate. Now, because t to the power d half is always going to be bigger than t to the power d minus 1 over 2, so the mass term estimate is also going to be decaying faster. So this is in particular also, so in other words, 1 over t to the power d half is always going to be less than or equal to 1 over t to the power d minus 1 over 2. Remember, we have a t is at least 2. Okay? So this means that in both situations, we can actually replace up to k over 2 L derivatives of phi measured in L infinity and up to k over 2 L derivatives of d phi measured in L infinity by the hyperboloidal energy of k over 2 derivatives plus d halves plus 1, right? This is the Sobolev sacrifice that you have to put in. And then we're using the rate t to the power 1 minus d over 2 because this is the worst of the two rates. Right? This is the slower of the two rates, and so we know that the phi term itself can actually be decaying faster, but we're just going to, for now, forget about that faster decay and just use t to the power 1 minus d over 2, the lesser rate, because if we can prove something using this situation, then this simplifies our argument a little bit, using a single rate instead of two. Okay, so we have that. Okay, and the fact that h is linear as s goes to 0 entirely comes from the fact that g is smooth and g of 0 is equal to 0. Okay, so this gives you that h of 0 is 0 and it's increasing and it's linearly increasing. Okay, good. So we have the following proposition, and this proposition is sort of the fundamental proposition that we're going to be using to control our higher order energies. Okay. All right. Good. So I just want to mention that, if you have any questions, you can post comments on the video or on this on YouTube. So I think it supports commenting, or send me an email. This is as usual. This is part of the class, and I know this proof is kind of long, complicated, very intricate, interlocking with different moving parts. So hopefully you can follow what's going on. But if you have any questions, feel free to ask. All right. So now we're ready with all these out of the way. We're ready to prove the global Wellposedness of the nonlinear Klein-Gordon and wave equations when spatial dimension d is at least 4. Then you ask me why d bigger than or equal to 4, and we already see why d needs to be bigger than or equal to 4, because remember what we want to do. We want to get energy control. And to get energy control, right, to get the correct energy fluxes, we need to be able to control the nonlinearity with these higher derivatives, right, in measured L2 in space and L1 in time. Okay, so in particular, we need this thing that just written down here in the previous proposition. We need this to be integrable in time. And when d is bigger than or equal to 4, 1 minus d over 2 is going to be, let's say, less than or equal to minus 3 halves. Okay, so when d is going to be equal to 4, bigger than 4, right, we have that this is t to the negative 3 halves power. And remember, t starts at 2. We never go down to 0. T starts at 2 towards infinity, and look at t to the power minus 3 halves. And if it's more negative than that, you're guaranteed to be integrable, right? Anything bigger than 1, strictly bigger than 1, is going to be integrable. So t bigger than or equal to 4 gives you sufficient condition for this to be integrable in time, right? So this tells you in particular, if it's integrable in time, this tells you that the L1 norm, right? If you integrate this L2 in space measure of the nonlinearity, if you integrate in time, you're not going to get something that's growing unboundedly. You're going to get this integral to be uniformly bounded. In particular, so again, key idea here is that if d is bigger than or equal to 4, right? This tells us that integral from 2 to infinity of Lj f L2 is uniformly bounded, provided these norms phi, right, on the right hand side are uniformly bounded, right? It's uniformly bounded, and that's the key idea. That's the key idea. Okay, if it's less than 4, then right, if it's 3, right, if d is equal to 3, then 1 minus d over 2 is going to be exactly minus 1. So this will give you a logarithmic divergence. If d is equal to 2, this gives you growing something like the square root of time. And in those situations, we run into the same sort of problem that we talked about earlier, where just assuming boundedness of the energy flux is no longer enough to prove that the energy flux of rho of phi is going to be bounded, because the energy flux rho of phi is now going to be, in the 3-dimensional case, grows logarithmically, and in 2-dimensional case, grows like the square root. But in 4 and higher dimension, assuming that phi has bounded energy flux means that rho phi also is going to have bounded energy flux by virtue of the fact that you have the L1, L2 norm of this L derivatives of f. Okay, so let's just state the theorem and just go through the proof. So theorem, d bigger than or equal to 4, we're going to solve box m phi equal to f. This has a unique global solution if the initial data is supported on ball radius 1, 0, and the hd plus 2 plus phi 1 hd plus 1 norm is sufficiently small. So the initial data, I want it to be measurable in the solar space hd plus 2 for phi naught and hd plus 1 for phi 1. D is number of dimensions, and we want this sufficiently small. Okay. So first, okay, let's first look at the homogeneous part, right? The solution is going to be so we're going to try to do the contraction mapping argument, right? So to do contraction mapping argument, right, there's going to be a homogeneous part and there's going to be an inhomogeneous part. Let's look at homogeneous part first. The homogeneous part is a linear part, and in this part, so we're going to look at the homogeneous part by thinking about the solution phi ring, right? Phi ring to be the solution to box m phi ring equal to 0, so the linear solution to the linear equation with initial data phi naught phi 1. So initial data at t equal to 2. Okay, so in other words, the corresponding capital phi naught, right? This is the part that's ut minus 2 of phi naught. Okay, good. So what we have is that there must exist some constant positive c bigger than 0, such that phi ring measured in the energy flux norms, right, is going to be bounded by initial data. This is just because of energy conservation, right? We have that the phi ring solves the homogeneous linear Klein-Gordon wave equation. Energy is conserved, so the energy flux ed plus 1 and curly ed plus 1 are both going to be constant. So in the first case, constant over t. The second case, constant over taus, right? So energy flux is constant, so it's really uniformly bounded. The question is only what is it bounded by? Now, my claim is that it's bounded by some constant multiplied by the ht plus 2 and ht plus 1 norm of the initial data. And this is because that if you look at the energy, what we have is that the energy on the right hand side, right, they're all bounded by what? By the energy flux, the initial energy flux governed by the solution phi ring with the number of L derivatives. Okay. Now this should be d plus 1 here, so we're looking at d plus 1 derivatives. Okay, so this here is the initial energy flux at t equal to 2, right? At t equal to 2, this is the initial energy flux of this is phi ring. Okay, of so j derivatives of phi ring, right? Now the key here is that Lj, right, is a combination of dt and dx, sort of a time derivative and spatial derivatives. Now what we're going to be using is that because we know that phi ring solves the linear wave equation, right? two time derivatives acting on phi ring is equal to one space derivative. So two time derivative becomes a Laplacian, right? And also, since we're fixed on the size t equal to 2, and we're fixed on the domain absolute value x equal to 1, this is bore radius 1, right? This is the support of phi naught and phi 1. This tells us that these expressions within here, dt phi ring, etc., these expressions can all be bounded by phi naught in hd plus 2 and phi 1 hd plus 1, right? Because what we're going to have is that every time we have two time derivatives, we can trade it for space 1. So this means that the final expression is always going to be ending up with exactly 0 or 1 time derivative. If it's a 1 time derivative, we're going to estimate it using phi 1. If 0 time derivative, it's going to be estimated using phi naught. Now, total number of derivatives that can head up, the maximum number is going to be, right, j, the number over here, plus 1. Now, j is going to be at most d plus 1 equals d plus 2. So we have either d plus 2 purely space derivatives or 1 time derivative and d plus 1 space derivatives. And so you have that the right hand side is bounded by this up to some constant. And this is structural constants coming in, and we're just going to absorb this as some c. Okay? So we have the following. So we have that the homogeneous term, right? If we have, so in other words, by making the initial data sufficiently small, we can guarantee that the homogeneous part has a norm as small as we want, using the capital E norm and the capital script E norm. Okay. All right. So that's the step 1. Step 2. So step 2. The key here is we're going to try to justify why we're looking at that particular number of derivatives. Okay. And so the idea here is that if we know that phi is in the intersection of curly ed plus 1 and Roman ed plus 1, right? So meaning that eventually in both norms, phi is bounded, right? And suppose we know that support of the function phi is within. So okay, we're only working in t bigger than or equal to 2, and I'm going to assume that the support is within this interior cone, this cone generated by the bore radius 1. Okay, then if we know that j is less than equal to d plus 1, what we have before is what? That Lj of f measured in L2, right, is going to be bounded by what? By here we have phi measured in Ej. This is the L2 integral of phi, and then inside we have the argument. This is precisely the proposition we proved earlier, right? About the L2 integral for f. Now the key here is that we chose d plus 1 over here because, let's look at the power here. For this power, we note that the following basic arithmetic fact, that d plus 1 over 2, like this is a fraction, you round it down, plus d over 2 round it down, this is equal to exactly d. Okay, again, you can prove this by induction. This is a Math 299 problem. So you have this. So this tells you that this fact here, right, this term here, is exactly equal to d plus 1. Okay? So this is self-consistency, right? Let's go back to what we had before. Before, what we have is that we have, if you take some, for any fixed k, right, then if j is less than or equal to k, then j derivatives is going to be bounded by ek on the right hand side and over here. And the key here is that if you look at these curly derivatives, right, you might end up for small k, right, for small enough k, then k over 2 plus d over 2 plus 1 might be bigger than k. And in situation, you might end up in a situation where inside here needs more derivative than outside here. And since the maximum number of derivatives you can control is k, right? This is so the maximum number of derivatives you can control for the solution is k, right? If you're going to control the solution by using the input data, so if you're going to control the output by using the input, where the input has higher derivatives, then this is not going to be a self-consistent argument, right? We want to use a contraction mapping argument. We want to have a mapping from some function space to itself, right? And in order for that to happen, we cannot actually be in a situation where to estimate k derivatives of the nonlinearity, we require more than k derivatives of the input. So luckily for us, because we have this pigeonhole principle, which tells you that inside here we have k over 2, and then the Sobolev inequality only loses you a fixed number of derivatives. This guarantees that if we choose k to be exactly d plus 1 or even higher, right, then the number of derivatives we need for the L infinity estimate is going to be fewer than the maximum number of derivatives I've taken, and therefore this can become self-consistent. Okay, and so this is a very important part in sort of small data theory for nonlinear wave and Klein-Gordon equations, and then this is basically sort of self-consistency check. Okay, so all right, so because of this, we can conclude that for any j less than or equal to d plus 1, j derivatives of f measured in L2 is bounded by, as I said before, phi in the curly E d plus 1 space and phi in the capital E d space. Okay, and we can use that if we use that h is linear as s goes to 0, right? This means that the following statement is going to be true. We have that there exists some c bigger than 0. So this c is not the same as c before just some constant. There is some constant c such that for every phi with phi's curly E norm d plus 1 bounded by 1. Okay, so the 1 here is not necessary. I mean, just any fixed number. Just a fixed number, right? This number is fixed. I have to fix 1 for the number for now. If phi in the curly E norm is bounded by 1, and for every single j less than d plus 1, you're going to have the Lj phi in L2 is bounded by c times the curly E norm of phi times the rectangular E norm of phi divided by t to the power d minus 1 over 2, right? And this the whole point here is just because we know that h of s, h is an increasing function, and I know that h is goes to 0 linearly, and therefore if for its argument, when its argument is less than 1, right? If you restrict to the domain where the argument is less than 1, there exists some constant c such that h is less than c times the input. Okay, and so this is basically what it is. All right, so we get this. We get the following thing, and here we're using and one interesting thing about this is that here we have a situation where we use that h is linear as s goes to 0, right? Now, if we go back to the initial assumption that we assume that f vanishes quadratically at origin. Now, if you're in a situation where actually f vanishes better than quadratic, if f is cubic, let's say, at the origin, somehow f the nonlinearity is cubic nonlinearity, there's no quadratic term either, then going through the same argument again, you'll see that h is going to become quadratic now. Okay, and if h is quadratic, then we can actually replace this. So in a quadratic case, so if f is cubic implies h is quadratic, and that implies, going back to this expression, we have actually the following slightly refined argument where Ljf measured in L2 is going to be bounded by, now we're going to get c, and then we're going to get, let's say equal to, what just happened here? Let's say equal to c multiplied by what? Now I'm going to move by phi, but since it's going to be quadratic, I can put this in d plus 1 squared. I can put the exterior one, still exterior, right? This the curly E one comes from the H norm. And now I have d minus 1 over 2 quantity squared. Okay. So what is the upshot of this? The upshot of this is that if f is cubic, if d is equal to 3, then d minus 1 over 2 is equal to 1, and square this will give you t to the minus 2. So in d equals 3, this gives you t to the minus 2 dk. And so everything that we're going to be saying about the general nonlinear case in d greater than or equal to 4 can also be said about d equal to 3 when f is cubic, and when d equal to 2, f is quartic. Okay, so the whole name of the game really is trying to push through sufficient decay, right, to make the nonlinearity integrable. And if you have a cubic nonlinearity, then the decay rate is going to be governed by the L infinity norm squared. If you have a quartic, it's going to be governed by the L infinity norm cubed. And so in the quadratic and in the dimension d equal to 2, dimension d equal to 3, where for generic nonlinearities, we're not going to be able to have enough decay to close argument. If we assume increased decay, we can upgrade the amount of decay that we have to guarantee that we actually have such an argument available. Okay? All right. So that's sort of an aside. Now going forward, so there is the argument. So now let's move on to sort of the next step of our proof for well-posedness. So let small psi be the first component of rho acting on phi dt phi. So remember now phi is one of these things that is this putative solution that we're going to plug in, right? So this is so basically I'm splitting capital phi into its components. Okay, and I'm going to assume that phi is in the phi itself is in this nice ed plus 1 and ed plus 1 where it's curly e and regular e. And we're going to apply rho to this thing, and then this is going to give a vector output, and I want to just denote by psi the first component of it. Okay? So, in other words, so psi and dt psi are precisely the solution to this system here. Okay, good. Now my claim is this. There exists some epsilon naught and epsilon positive such that if we know first support of phi, so the input, right, the input to this guy here, right, this is not the initial data now. Initial data is already fixed. The support of phi is inside this light cone t bigger than or equal to x plus 1. And we're going to assume that the initial data is less than epsilon naught. And we're going to assume that the phi, right, that we're looking at. Remember, at this point, right, we're looking at concentration mapping argument. This phi is just a putative solution. This phi has nothing to do with initial data right now. Phi is just some function, some space-time function. And we're going to try to show that within the class of space-time function, there exists a solution. So phi has nothing to do with phi naught and phi 1. Okay? We're just going to say that phi is some arbitrary thing such that phi in the curly E norm and the rectangle E norm, okay, both are less than epsilon. Okay? And then we're going to assume that the initial data, which is independent of phi, is less than epsilon naught. If we have that, I'm going to claim that the generated solution psi, right, from the rho mapping, is going to have curly E norm and curly E and regular E norm both less than epsilon. Okay, so the epsilon are the same epsilon, showing that we have a self map. Rho gives you a self map of the ball radius epsilon in the E space and in both E spaces, the curly E and regular E spaces. Okay, and furthermore, we're going to have the support of psi to be contained within this cone. Now, the second condition, support of cone psi being contained in the cone, is essentially automatic because it follows from finite speed of propagation for solution of the wave equation. We know that the data is supporting ball radius 1. We know that homogeneity is going to be supported in this cone, and therefore the solution is going to be supporting the cone also. So there's nothing much to say about that. So subordination is automatic from finite speed of propagation. We're focused on, however, verifying that we have the two norm conditions satisfied, that psi measured in the regular E norm and the curly E norm are both less than epsilon, provided that epsilon naught and epsilon are sufficiently small. Okay? So how do we do that? Okay, we have, so for the regular E norm, what we're going to do is we're going to apply the L2 estimate to Lj psi. What do I mean by that? Okay, let's go. Let's first see the picture. So J here is less than or equal to d plus 1, right? This is a number of L derivatives we're going to take. So we're going to take some number of L derivatives of this psi, right, this generated solution. We're going to try to estimate its energy, right? Because this is Ed plus 1. Ed plus 1 is precisely the maximum of the energy flux through constant T slices. And I want to sort of, if I can prove a uniform estimate of the energy flux, then we're done. So to prove energy estimates, to prove estimates on energy flux, we use energy estimates, right? This is sort of a tautological statement. So what does psi solve? Psi is a solution of the box M of psi is equal to F, and F is over phi and d phi, right? These are the input function that we put in. So we should consider that as fixed for now. And initial data is phi0 and phi1. Okay. So the L2 energy estimate that we had before, right? Exactly the same one that we used for studying the local Wellposedness, right? Tells us that psi of ED plus 1 is going to be bounded by what? By the ED plus 1 norm of the homogeneous solution, which is essentially what we get from the initial data, okay? Plus the integral from 2 to infinity of Lj of f acting on psi, Lj acting on f, right? This is basically just the taking the L2 of this. We know that so basically by linearity, right? By linearity, we have that Lj of psi is equal to Lj of ut minus 2 v0 minus Lj of this integral of ut minus s 0f, right? So it's something like this, and we're just taking the Lj acting on everything, and we'll take the Lj we acted in because Lj commutes with the wave equation. It commutes with the wave operator, and so we can actually put Lj into this. Okay. So the Lj can be transferred to act on f, and we're going to have that taking the estimates. We have precisely this guy over here. Okay, so we'll take L2 in space and then suprema in time. Okay, so we have precisely this thing over here, and then based on what we had before, we know that Lj of f is going to be bounded by what? By epsilon squared, because we know that Lj of f is bounded by, where did I have this? Over here. If both of these inputs, the curly E and the regular E, are less than epsilon, right, we get C times epsilon squared divided by T to the power D minus 1 over 2. Okay, so the homogeneous term contributes C times epsilon naught. This is what we did in the first step of this proof. In this term, just to disambiguate, we use C prime for the constant that comes up. C prime times integral from 2 to infinity epsilon squared over T to the D minus 1 over 2. Basically, the idea here is that, right, for every single fixed T, which will be integrating from 2 to t, right? We'll be integrating from 2 to t here. But since we're taking over the supremum over all possible t's, right, then we can just take t to infinity, and this will definitely bound every single one of the subintegrals. So we can do the integral over here, and we take this, and we see that this gives you c times epsilon naught plus c double prime times epsilon squared. Okay? All right, and here we use the fact that d is equal to 4, so that this guy is integrable. Okay. So as long as I choose my epsilon initially, remember, what is C and C prime? C here is the C that showed up in step 1. Yes, in step 1, the homogeneous estimate, right? This is structural constant coming from converting the initial energy flux for the Lj derivatives into an estimate based on HT plus 1 norm, right? This does not depend on the solution itself. And then we have C prime, which is the coefficient that comes up over C prime is the coefficient that comes up over where? Over here. C prime is this coefficient over here in this conclusion over here, the purple highlighted thing. And this C prime is entirely constructed out of the properties of this function h, and this function h is entirely structural based on the form of the nonlinear function f, right? It depends on what this f looks like, but does not depend on what's put into this f. So h is a structure constant that's independent solution. So these are functions independent solutions. They're constant depending on the equation, but not on the solution. So this tells, and then once we integrate 2 to infinity of this t to the d minus 1 over 2, we get another constant, so we can absorb into here to call it c double prime, right? So c double prime is c prime multiplied the integral from 2 to infinity of this t to the d minus 1 over 2 in the denominator. Okay, so if we can choose, so this means that c and c double prime are independent of the thing they're trying to plug into the contraction mapping argument. So if we can choose epsilon naught sufficiently small, such that c epsilon naught plus c double prime epsilon squared is less than epsilon, then this energy will be controlled, right? Remember, so c and c double prime are fixed constants coming from the equation, right? So, for example, one way to do this, we can choose epsilon less than 1 over c double prime times 1/2. Okay, and then after we choose this epsilon, we can choose now epsilon naught to be less than, let's see, 1 over 2c 1 over 2c times epsilon. Okay, then if you choose this, then this first term becomes less than 1 over 2 epsilon, and this also becomes less than 1 over 2 epsilon, and they add up to less than epsilon. Okay, so basically, given the constant c double prime and c, we can choose epsilon naught such that this inequality is satisfied, and this will guarantee that c measured in the ED plus 1 norm is going to be less than epsilon, and so this will prove the one of the two statements that we have here. Okay, so now we're going to next tackle the curly E norm. For the curly E norm, right? For the curly E norm, what we're going to be doing is that we're going to be looking at the energy flux through sigma tau, the hyperboloid of psi. So we're going to look at energy estimate for psi through and looking at energy flux through sigma tau. Okay, so to estimate the energy flux through sigma tau, right? What we're going to do is we're going to use the energy estimate, which is the squared version. So we have the energy flux through sigma tau, right? It's going to be bounded by the initial energy flux plus, right? This is the version where we essentially looking at the energy current, right? This is you look at energy current, its divergence is equal to inhomogeneous term times dt of the solution, right? And then we look at this, and then we look at and then integrating this gives you a boundary terms equal to bulk integral, right? So this is the energy method, and we look at this, then we see that energy flux. So this will be like something like a square. This will be roughly the square norm of the curly E norm through sigma t. Is going to be bounded by initial data. And the initial data is also the initial energy flux. So this is again the same thing, which we controlled before by epsilon naught, plus the integral of the space-time region between the initial data slice and the sigma tau slice of the inhomogeneity LJF multiplied by dt of the solution. Right, here we're using the fact that of course, here we're using the fact that LJC solves the equation LJF. Okay, so essentially what we're doing is multiplying by dt LJC integration by parts, and this is what we're going to get of the energy. So here the gray blob just saying that we're integrating over the space-time region between 0 and sigma tau. Okay, so the key here, however, is that we're trying to integrate this thing on the shaded region. Now, so first we can take the absolute value. We can put in absolute value, make it bigger. Okay, so put in absolute value and put the absolute value inside. And once we put absolute value inside, then this is an integral over some space-time region. We can replace this by integral over the entire region t bigger than or equal to 2, and going to get bigger value, right? So the integral over the space-time region of this thing is going to be bounded by integral over t bigger than or equal to 2 of the absolute value of the things. And now what we can do is that since we're integrating over the entire part between t bigger than or equal to 2, we can split it up first into a spatial integral and then do a time integral. On a spatial integral, right, we have integral of product, and we can use Cauchy inequality and split it into L2 times L2 in space. So this is L2 of RD. Okay, and now integrating time from 2 to infinity. Now this first term over here happens to be something controlled already, right? This term here, dt of LJC, is part of the normal energy that we control in the first part of our argument, right? This is the energy flux. This is part of the energy flux through the constant t slice. Okay, and so we can control this first term by the regular flat energy flux norm that we have. Okay. On the other hand, we have this other term that's left over on the left hand side. This term we have left over on the left hand side. We're just going to have to do it by hand. And what we have is that we again have this integral from 2 to infinity of LJF in L2, and this is precisely what we estimate already over here. This is the same thing as this term over here, right? And so we have already established this is something like C double prime times epsilon squared. Okay, so this is C double prime times epsilon squared multiplied by the epsilon coming from this, right? This is epsilon squared, so we get C double prime epsilon cubed. So we have that the total contribution from the inhomogeneity, right, is going to be no more, again using the fact that we have a integrable in time decaying weight. That gives us that the total integral from there is going to be no more than C double prime epsilon cubed. The data bound, initial data bound, we can use against the homogeneous argument, the homogeneity argument before, which tells us that the data is going to contribute something like C to the epsilon naught, but since this is the squared energy, right? So we have to be C squared epsilon naught squared. Okay, so now we just need to choose epsilon naught even smaller, such that C squared epsilon naught squared plus C double prime epsilon cubed is less than or equal to epsilon squared. And you can do this in exactly argue this in exactly the same way by choosing epsilon sufficiently small first, and then choose epsilon naught even smaller, and this tells you that this is going to be bounded by epsilon squared. Okay, and if the energy flux is less than epsilon squared, then the energy is going to be less than epsilon. Okay, so what we have here, right, is that if we choose so this tells us what? So this tells us that the claim that we have is now proven. Okay, so it tells us that if I choose the initial data sufficiently small, then I can find a sufficiently small ball in the space curly E d plus 1 intersect regular E d plus 1, such that my row mapping actually becomes a self map of this ball. Okay, so we're half the way there towards continuity. We have already proven that this is a self map. So the next step to do then is to argue that we actually have this is a contraction mapping. So let's go down to step 4. My claim is that if epsilon naught and epsilon are sufficiently small, then this mapping is contraction. Why is that? Well, remember that we're looking at this semi-linear problem where we're using the row mapping, right? And so if we have two different inputs, phi and phi tilde, into this row mapping, right? When we take we'll take rho phi minus rho phi tilde, right? Then the homogeneous part entirely drops out. Homogeneity entirely drops out. Okay? So the homogeneity entirely drops out. So we just need to essentially make epsilon sufficiently small. Okay? So this means that if you want to measure the difference rho phi minus rho phi tilde in the ED plus 1 intersect curly ED plus 1 norm, right? We just need to look at essentially the inhomogeneities F, the inhomogeneity corresponding to phi and phi tilde, right? Take their difference and measure it in the norm that we care about. Okay. And so what we're going to do is going to use the same argument that we did before when we talked about the linear equation, the Doppler-Wellposedness result. So we're going to use that f phi minus f phi tilde is going to can be written as a integral derivative, right? This is sort of the same mean value theorem kind of argument, right? This we had done already before, so I'm not going to go too much into this. So the difference is going to be so just by you can think of this as draw a line between phi and phi tilde, a straight line, right? And take its derivative relative to parameter on a straight line and integrate it along the line. And this will give you that by the fundamental theorem calculus, this will give you integral from 0 to 1 of the derivative of f multiplied by phi by the slope of the line. And the slope here is going to be what? If you draw a straight line between phi and phi tilde, the slope is exactly going to be phi minus phi tilde and d phi minus d phi tilde. Okay. So we have this thing here. So this is the slope. This is the function, so the slope or slash speed, I guess, right? And this is the function f prime, and you integrate this, you get evaluate the difference of f between endpoints. Okay, so if you look at L derivatives acting on this difference, then we here have a product, right? So all I think on this thing, we're integrating over respect to s. So I can put the since this is a finite integral on a finite interval, and everything inside is sufficiently nice. What we can do is I can just put a derivative inside, and we put derivative on the inside into the integrand. Then one of two things can happen: either the most number of L derivatives is hitting on the linear term on the end, the difference, phi minus phi tilde and d phi minus d phi tilde, or the most number of L derivatives is going to hit on one of the arguments to f prime. Okay, so there's two cases. When most of the derivatives hits on the final term, right, what we can do is what? I'm going to put most of the derivatives on the final term, and I'm going to put that term in L2. Okay, I'm going to put that term in L2, and then I'm going to put the rest in L infinity. And so, because this is again some derivatives of f, right, replace it by this function h using the same way we did before. This is just some h is just a function that controls the size of f in terms of its input, right? So we're going to have that. We can put the input to f prime, which is s phi plus 1 minus s phi tilde, measured in the curly E norm, right, with some decaying factor, right? This is the L infinity norm over there. And then we have phi minus phi tilde measured in the rectangular E norm. This is because we're integrating the difference here. We're integrating this difference, right, in L2. And we have some number of a large number of L derivatives hitting on it. In case 2, on the other hand, what we're going to do is we're going to put the L2 term where most of the L falls, right? L falls on some term of this form. So what we're going to do is that we're going to have one term where most of this falls. This is in L2 in space, and this gives me the rectangular estimate. This is the energy flux of that particular object. Okay, I'm going to put phi minus phi tilde, right, in L infinity. So this term over here, this term, get placed in L infinity. Because this has not the most number of L derivatives, it has at most 1/2 the total number of derivatives. So its L infinity norm can be bounded by this guy, by the difference in the curly E norm with a 1 over t to the power d minus 1 over 2. Okay, this is again using the Goebbels-Sobolev inequality. And then we have the remainder terms that shows up in f prime. Those we're going to bound in L infinity. And this is going to give me another smooth function, h prime. H prime is not necessarily a derivative of h, just some function which is kind of like a derivative of h, because whereas before h here, right, h here is the bound on the function f prime, and we know that because f is a function that vanishes quadratically, we're going to f prime is going to vanish linearly, right? So we're going to have the f prime is going to have linear vanish linearly in its argument, and which was why h is going to vanish linearly too. Now here, if we look at the this f prime which vanishes linearly, if we look at the higher order derivative term on it, we put that in L2. The remaining thing has to be just bounded near 0. So h prime of s is going to be a big O of 1. It's going to be bounded near 0, but it's not going to be necessarily going to 0. But the key thing is that it's bounded, right? It's bounded. So it's this bounded function near 0, we can just replace by some uniform bound. And so therefore we have that, in fact, that we have, again, a 1 over t to the power d minus 1 over 2 multiplied by this. So the key thing here is what? Is that if you add these two together, right, this tells you that Lj of f minus f tilde, right, in the end, if you look at measuring L2, this is going to be the difference, right? We have the difference here. The difference measured either in curly E space or in the rectilinear D space, multiplied by a linear factor of s phi 1 minus s phi tilde, measured either in E space or curly E space. Okay, multiplied by a decaying factor t to the d minus 1 over 2. Okay, so now if you integrate this from t equal to 2 to infinity, this gives you a constant coming out. And so this tells us that if you look at So let's say psi is the solution to, so psi is the solution to rho of phi, and then psi tilde similarly. If you look at this, measured in E d plus 1, okay, that's it, measured in E, sorry, let's measure this in E d plus 1, right? This is going to be bounded by integral from 0 to, not to 0, integral from 2 to infinity. Integral from 2 to infinity of Lj derivative sum over J. Lj derivative acting on f of phi minus f of phi tilde, right? And this is going to be L2 in Rd times dt. Okay, and we have something like this, right? And from what we had before is that this is actually going to be bounded by some universal constant times, okay, times either we're going to have psi, sorry, not psi, this is going to be given by v minus v tilde curly E norm times v curly E norm plus v tilde's, not curly E, this will be, should be rectangular E norm. Okay. This is rectangular E norm, plus v minus v tilde rectangular E norm times v curly E norm plus v tilde curly E norm. The whole thing divided by t to the power d minus 1 over 2, integrated from 2 to infinity dt. Something like this, okay? Using the case 1 and case 2 and as we did before. Okay, so now this integral can be taken away because we know that the integral converges. So this integral goes away, we can add it, we just modify the constant c that shows up to account for the integral, okay? So we have something like this. So this tells us that provided, and you can do you can do a similar thing for the curly E norm. You can have same idea, you get same quantity. You get also that the same for phi minus phi tilde in the curly E norm, and you'll find pretty much the same thing. And so what you're going to see is that if you look at this thing, right, it tells you that phi minus psi minus psi tilde measured in both ed minus plus 1 and curly ed plus 1 is going to be bounded by the difference measured in the corresponding norms multiplied by phi and phi tilde measured in the E and curly E norms. So if I take phi and phi tilde to belong into ball of some ball radius epsilon, right, near 0 of ed plus 1 intersect curly ed plus 1, right, for sufficient 1 epsilon, this is giving 2 epsilon coming out, and so this is going to be less than equal to 2 epsilon c times phi minus phi tilde plus phi minus phi tilde in the one of them is curly E and the other one is rectangular E. So let's erase this, make this the rectangular E. Okay, and we see that if epsilon is sufficiently small, this guarantees that we have actually a contraction mapping. Right, we just need to make sure that epsilon is less than 1/4 or something. 2 epsilon c is less than 1/4 or something like that. Okay. So now we have this. Right, so this is good. So with contraction mapping, then this tells us that rho is a contraction mapping, right, for epsilon sufficiently small, right? Now for so why do I need epsilon not sufficiently small over here? Because we need, well, if we make epsilon smaller to make this mapping here, right, a self-consistent mapping, right, to make this claim hold, remember we had to choose epsilon to be small enough relative to, sorry, epsilon not small enough relative to epsilon, because over here when we choose epsilon for the closure relation, right? When we choose, sorry, where did I do that? I did over here. When I choose when I solve this inequality to get closure, right? I need to first choose epsilon and then choose epsilon naught to be smaller than something times epsilon. Okay, so epsilon is now going to be adjusted based on epsilon, and so by choosing epsilon sufficiently small down here, necessarily you have to choose also epsilon naught sufficiently small. And so this tells us that for epsilon naught sufficiently small, we can actually make this a contraction mapping, make rho a contraction mapping on a ball or ball radius epsilon within the E intersect curly E space. And this tells us that we can apply the fixed point argument and finally conclude that we actually have a solution to the nonlinear equation. And by virtue of our construction, the solution is going to be global in time, and it's going to be unique because of the contraction mapping argument. And in fact, it's going to depend Lipschitz-ly on initial data simply because we are proving this using contraction mapping. Okay? So all right, so let's pause here. This is a really long lecture. I really apologize for the length of this one. But with this we proved we gave essentially the complete outline for the proof of the global well-posedness of the small data wave and Klein-Gordon equation, small data small data global well-posedness for the semi-linear wave and Klein-Gordon equations for general smooth nonlinearity in dimension d bigger than or equal to 4, and this also, as I said before, also gives us the proof for the case where you have cubic nonlinearity when d is equal to 3, and quartic and above nonlinearity when d is equal to 2. Okay. All right. Unfortunately, in d equal to 1, you cannot say anything because d minus 1 over 2 is going to be equal to 0, and there's absolutely nothing that you can, taking powers of t to the 0 is going to give you t to the 0. So for one dimension, nothing can be said. Okay, but for 2 and higher dimensions, we can say that with different types of nonlinearities can sometimes give us global well-posedness results. All right, so let's pause here, and we'll have a few concluding remarks I want to wrap up in the next lecture.